Okay, sorry, I thought I was going to get through that whole problem in one video. All right, so the side, you know what, I could write what I'm doing over here. I'm saying, I'm trying to find out, is CD over CA, that would be one side, CD and CA, is that proportional to the other one here? The other sides I have here are CE and CB, if you look carefully. CE would have to go with CB. And that would make side angle side. And it's a little weird because, we're not talking about sides that are equal here. We're talking about sides that kind of go with each other in these two different triangles. So is that really equal to CE, which is 8, over CB, which is 12? Is that really true? And I think it is, because if I try to solve that, reduce this fraction, I get 2/3. Reduce this fraction, I get 2/3. So that's yes. So this is yes. Everybody's happy, and this is yes. So that's a great big yes. They are similar because I checked out these numbers and they do make the fractions equal. The angle between them is the same. Yay, I've got side angle side. Okay. This one, just looking at what we've got here. Remember our list here. I didn't do this last time, but the possible choices for similarity sets are those. And notice how everything here is all labeled in sides. I don't have anything about angles. I don't have any angles shared. I'm gonna go for this one here. So if that's going to be true, I got to find, not only do I have to find two sides that are, like a side and a side from each triangle that's proportional to it. I got to find all three in the same fraction. So when I do that, and I'm looking, I have all the sides measured. I like to go, if it's going to be true, short is going to go with short. When I set up these fractions, and I'm thinking, okay, which twisted way might these triangles go? I kind of go short with short should equal medium with medium should equal long with long. That's the only way this would ever be possible. So what's the shortest side of this triangle here? That would have to be 3. And then later we can figure out the letters and see which way they go. 3 is the shortest side up here. The shortest side in the bottom triangle here would have to be 6. The mediumest side in the top triangle would be 4. The mediumest side of this bottom triangle would be 10. The longest side of the top triangle is 6. The longest side of the bottom triangle is actually 12. Are all those fractions equal? No, that's half. That's half. This ain't half. So this is a great big no. We don't have side, side, side. Okay. All right, there's at least one angle in this set. We have an angle here and an angle here. So we're either talking about angle, angle, or we're talking about side, angle, side. But there's no other sides labeled here at all. And I don't know if either of these things are midpoints. Usually midpoints actually aren't even helpful because I'm not looking for things that are congruent. I'm looking for things that are proportional. So you notice, as compared to those chapters we did on congruent triangles, you see a lot of numbers of sides here because we're looking for fractions that are equal. And stuff that's marked congruent isn't helpful. Notice this is all in numbered sides also. This doesn't have anything for sides. It just has angles. So I'm kind of thinking angle, angle. The triangles here would be like this little one here, MPQ, and then the big one, MNO or something. They might be twisted up, especially because these kind of seem like they're flip-floppy. In the two triangles, just like in the first example, I do have this angle that is in common that's in both triangles. So let's see if we can line these up. Because I'm thinking it's going to work by angle, angle. I have a a two rainbow angle and this shaded gray angle in both triangles. So I'm just going to go ahead and say yes. But the hard part's this. Angle M in one triangle has to go with angle M in the other triangle. P in one triangle has to go with O in the other triangle. And then the last one should just fill itself out. Q is the other point and N is the other point. So that's all there is to that one. All right, I have a 60-degree angle and a 60-degree angle. Great. So there's an angle. This looks like side angle side up here. Oop, this doesn't look like side angle side over here. So that's a problem. Think about this, though. If you got a 60-degree angle and an isosceles triangle like this, if it's an isosceles triangle, I know these angles are congruent. If this one's 60, what are these? Well, they have to be congruent. They have to add up to 180. So guess what? It turns out these are also 60. So what kind of triangle is that? File that away. Now look at this. I have another isosceles triangle. If this angle is 60, this has to be 60. If this is a triangle, it's 180, so this is also 60. So I've got two equilateral triangles on my hands. I don't know the lengths of any of these sides. I just know I have equilateral triangle number 1 and equilateral triangle number 2. Well, here's the deal. I know I have 60-degree angles everywhere. I have angle, angle. Should I want to talk about it that way? Because there's an angle here and an angle here and an angle here and an angle here. And the other thing is these things are completely twistable and they'll be the same kind of shape. So I could call this. So by the way, I do have yes because I have angle, angle. You might be asking, well, does that mean every equilateral triangle is similar to every other equilateral triangle? And yes, yes it is. All squares are similar. All regular hexagons are similar because they have the same angles and they have the same relative size of their sides. So yeah, all equilateral triangles are similar, so we're done. I don't know the scale factor, but it doesn't matter. I know there is one because of AA. All right, so what's the similarity statement? You know what? It doesn't matter because these things are completely twistable. Their 60-degree angles are going to line up no matter what I do. Let's just say GHI. Thought I was going to go alphabetical, didn't you? Let's go KLJ. It really doesn't matter. You could write this like 9 different ways and it would be fine. For this example, because they're equilateral. All right, last one of these. I got a 60 and I got a 59 and a 61. You're probably thinking, well, that's dumb. They're not going to work out. These are different. But wait a second. What's the last angle? If this is 60 and this is 59, to complete the triangle, they do this all the time in books and SATs and that kind of stuff. Figure out the third angles of the triangle because of the 180, and lo and behold, they have all the same angles. So yes, we have another AA in our hands, and now we have to be careful because they're not all 60 anymore. They're slightly different, so we have to line these up correctly. So if we say A, B, C, A goes with F, B goes with, that's the 60, that's E, and D is the other point. So that's how they have to line up. Okay. They're telling us it's similar, and they're asking us to apply that. So if they're similar, then I know all those fractions are going to work out. All the proportions are going to work out the way these say they correspond. So find x and y. So this is kind of like the first problems we did. All right, I kind of like y first. Again, I want from the small triangle, which is, ADB, that's the big one, that's the small one. Between the two triangles, I want to find one that's all numbers first. Also, don't forget about this. This is a common feature of these kind of problems, is you have to think about that kind of stuff because that is the side that we think about in AD. 7 over ED. Oh, let's just start writing that. 7 is to, AD is to ED. Now what's ED? 4. Oh, look at that. I found my scale factor right there. All the fractions that I do from the big triangle to the little triangle, they're all equal to 7/4. Hallelujah. So y over 8, 8 over y, 8's from the big triangle, y is from the small triangle. That has to equal 7/4. Oh, let's just do this one. Why are all these so nasty? Oh my gosh. Well, you know what? Here's my retaliation. I'm not going to reduce that to a decimal. All right, so y is 32 over 7. It's like 4 point something. And then what's the deal for finding x? Okay, x isn't, this is kind of annoying too, but it's a common feature, so get ready for it. X is not the length of a side of one of these triangles. X is the piece of, BD. BC isn't part of a triangle. Like there's no B and C in any of these triangles. So BC is just kind of a portion of BD. So remember the way I'm doing these fractions here, I'm doing big over small. BD over DC is the thing that has to equal 7/4. That was my scale factor, remember. So BD, oh wait, how do I draw BD? Or how do I express BD? DC is not, or DC is 3. That's easy. That equals 7/4. But I can't just put x here because that's not BD. BD is this, just like I did this with the 3 plus 4 equals 7. 3 plus x equals, well, it equals 3 plus x. So I have to say that. That's the length of all of BD. Then you got to do this crazy cross multiplying with this thing sticking in here. So be careful how you do this. You got to remember to multiply the whole, whoops. Yeah, be careful how you do that. We're multiplying the entire top times the, bottom on the other side. So this is 21. That's not bad. This is 12 plus 4x. If you don't do that carefully, you're not going to distribute correctly. But remember that whole cross multiplication. We spent a lot of time on this last unit or last lesson. Just be careful. You can do it. So again, I get weird fractions, but that's okay. I've solved for x and y. Okay. Suppose I want to estimate the height of Marina Bay Sands. And yeah, because you don't want to crawl up there and then drop a string and that kind of stuff. So I measure my shadow at 48 centimeters and I estimate the tower shadow to be 58 meters. If I am 1.6 meters tall, what's the estimate for the height of the hotel? Okay, sketch a diagram. Well, the deal is we can assume on these shadow problems. So here's you. I didn't draw that very well. Let me make the drawing and then I'll show you what I mean by it. Okay, here's you. Here's Marina Bay Sands. I don't know if I do these triangles kind of the right proportionality, but you get the idea. The deal with shadows, which is kind of cool at the same time, is we believe you can kind of think about this. If here's the building, here's the shadow. This is connecting the tip of the shadow to the tip of the building. This is kind of the direction. If you were to stand here and look straight at the building, you'd be looking straight at the sun. I don't advise doing that. But from this point to here, this is kind of showing about the direction of the sun. At the same time of day, this should be the same direction. We consider the sun's rays to be parallel, which I know is slightly off because they intersect with the sun, but that's 93 million miles away. Close enough to be parallel. So we have corresponding angles here and here. Those are corresponding angles if those lines are parallel. And we talk about heights in terms of straight up and down. Wow, I made that small. So right there we have similar triangles because we have angle. So that sets this whole thing up. I decided to do the whole thing in meters because we've got this centimeter meter problem. I changed the 48 centimeters to meters, and that's not illegal. Okay, so then we have similar triangles, and we just go to town. There's a lot of kind of assumptions you have to think about to get that set up, but you know what? There's a lot of shadow problems, and they're all exactly the same, and you get used to them very fast. So let's just do the thing. 1.6 in one triangle kind of goes with x in the other triangle, and 0.48 in one triangle goes with 58 in the other triangle. Time for some algebra. And I just cross multiply. Of course, the decimals are a little yucky, but I cross multiply, and I found out x to be something of 193.3. I have no idea if that's accurate for Marine-based sands. Also, you notice my triangles are completely out of proportion. If this is 58, this is what? 193. Well, look how I do this. This is 1.5 meters. This is half a meter. So yeah, of course they're similarly out of whack, which is, you know what, fine. It still works for the algebra, even though, and for the calculation, even though it's a bad picture. You're used to that by now. So here's a little summary. Those are the three in one diagram there. I like how they do this because, again, getting, in this little scheme about similarity, what's equal and what's proportional, it's kind of tricky. Sides are proportional, angles are equal. All right, I'll see you in class.